Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm very happy to introduce Pierre Ganti to you. Pierre's been visiting us for about a week. Today is his last day here. He's visiting from India in Madrid. What does India stand for, Pierre?
Institute of Madrid in Advanced Studies.
In Advanced Studies.
Yes.
It's the institute devoted to computer science topics?
I mean, there are like several of those, but EMDR Software Institute.
India Software Institute, right. So yeah, Pierre works on verification and automata theory and these kinds of topics, and today he'll tell us about some work he's been doing in the past few years.
Okay, thank you, Shaz, for the introduction. So it's going to be an overview talk of some of my work in the last years, and just to plan the picture, so I'm doing verification. And what I call verification, it's a reasoning which is precise and exhaustive about the behaviors of the system. And in particular, I'm interested in infinite state systems, such as sequential programs or concurrent programs. And I'm going to speak about both kind of system in this talk. And I'm interested in algorithmic techniques, which means that the reasoning is fully automated. There is no human assistance. And in those last year, I've been focusing more on the precise aspect of the verification, giving up on the exhaustiveness of the analysis. So here are two important problems. There are safety verification for programs, so for procedural programs where you have only one thread of execution, and safety verification for multi-threaded programs. So first we start with bad news, is that in general both those problems are undecidable. And even if you take a drastic assumption, like assuming that all the data in the program is finite or Booleans, there in the sequential case, you obtain decidability, although the problem is X time complete, which means it stands very high in the complexity hierarchy. And in the case of multi-threaded execution, it's not helping there to do this assumption. So this is why I want to study under-approximation. So as over-approximation do it, so here we want to sidestep the problem of undecidability or high complexity of the problem. So, and when I say that we want low complexity problem, I'm referring to classes like NP or P-space. So here in this talk, I will explain you how to obtain under-approximation technique. And in the sequential setting, I will give you a restriction on the control flow of the program. And in the concurrent setting, we will restrict the communication between the different threads. So, and what are under-approximation good for? So one obvious application is to use them in bug finding. One which is less obvious, and I'm going to talk a little bit about this, is to refine your abstractions when you are in an abstraction refinement setting. Okay, so the first part of my talk, I will tell you about the contribution I have done in the context of multi-threaded program. And then in the second part, we will go to sequential programs. So let's start here with a safety verification problem. So you have this multi-threaded program. I kept it very simple for the presentation. You have two threads, and those two threads, they communicate through the shared memory. And in the shared memory, we have one variable, this variable bit here, which is shared among the two threads. And the question that you ask here, for instance, is the line of code labeled by error reachable? So before starting with algorithmic techniques, let's just have a dry run by hand somehow. And I'm going to use the following model of execution. So I'm using this send clock here to say that T2 is not going to do anything, and the active thread is T1. So if we start to execute T1, for instance, we assign false to the bit here. We arrive at the conditional. We evaluate it. It evaluates to false. So we jump to the else statement, and then we jump back to line L1. So now say that I go to the if statements, and here I decide, because I'm the scheduler of the system, I decide to perform what is called a context switch. So and what I'm going to do, I'm going to change the identity of the thread that's active in the system. So I move the send clock to thread 1, meaning that thread 2 is now the active thread. And also what I have to do, I have to let know thread number 2 what is the value of the shared variable of bit here. So I copy, if you like, the value of the variable in the shared memory, which is false. Now I run thread 2, which just keeps assigning true to bit. So I execute this. And again, I decide that a context switch happens. So now I rewrite the shared memory, and I have that the value of bit is equal to true. I resume the execution, which was about to evaluate the conditional. Now the conditional evaluates to true, and I can reach the error statement. Okay, so my point here is to tell you that, to show that even for very simple program, that's a very difficult problem. But I guess all of you guys know that in concurrent settings, the problems are difficult. And the decidability picture is not really good because even if you assume finite data, you have undecidability. So what people have done, and by people I mean by Shas, for instance, is to restrict the scheduler. We will obtain decidability by restricting the scheduler of the system. And the idea here is that the scheduler, it's the agent that controls who writes and what is written on the shared memory. And so this sequence here is a schedule. So and how you should read it. So the schedule says that first T1 runs, and then at the switching point, bit is the value true is written for bit in the shared memory. Then T2 runs. Then at the switching point, the value of bit is false. So it has been shown that when you restrict the scheduler to a finite set of schedules, the problem becomes decidable, no? The safety verification problem under the restriction of bounded schedulers. So for instance, you allow like k writes or k context switches. So what it means, a context switch, it means that any of the thread can run, and then anything can be written to the shared memory, and you allow this to repeat at most k times. So in this fashion, by this expression here I've defined the set of schedules that corresponds to k context switches. And the way I have contributed to this line of work is by extending the class of schedulers, not to bounded schedulers, but to unbounded schedulers. So of course I cannot extend it to arbitrary unbounded schedulers. I still have to pick a restriction, to find a restriction, because the problem is undecidable. And this is, for instance, the kind of scheduler I can allow. Is the arbitrary repetition of this schedule. So that's one instance. So, and in general, what I'm allowing are schedulers schedules that are captured by a regular expression of this form. So you will see this kind of regular expression throughout the talk. And to make things clear, I call them bounded expressions. So in our work, what we have shown, so we have done all the reasoning in a language-based setting. So and to do this, what you do is that you take your program with the two threads, and you translate each of the threads as a context-free language, or rather a device that generates a context-free language. such as pushdown, automaton, or context-free grammar. Now, if you look at the problem from that perspective, the language perspective, you have the following picture. So the general problem to know if the error statement is reachable, it boils down to ask if the intersection of two context-free languages is empty or not. So, and see here I put a third ingredient, this sigma star. It's to somehow, you could remove it, but the way I mean, if I choose to put it, it's to emphasize the fact that the scheduler can be arbitrary here. There is no restriction on the scheduler. So, and that makes the problem undecidable. Now, when you start to take restriction on the scheduler, like bounded context switches, then it boils down to look for a witness of non-emptiness of the intersection in this set, like the words up to length k. And the case of bounded expression, what is called pattern-based verification in the paper. So here you look for a witness of the non-emptiness of the intersection inside a set, which is potentially infinite, and that's captured by this bounded expression here. And with those two restrictions, here you obtain decidability, and you can even show that both problems are in NP. Okay, so this work, we have published a paper at Popple about that, and we are preparing a journal version. So the contribution from a theoretical point of view, we have done a complexity, in detailed complexity analysis of this problem. And here are the parameters that we have been playing with. Some of them seems very natural. Some other you will see are a bit more sophisticated, say. So as a parameter, we have looked at the number of threads in the verification problem. So the second parameter, PR, here is the maximum number of procedures for each thread. There is the size of the thread, and then the two last parameters are a bit less natural. So there is the size of the bounded expression that you're looking at, and finally there is this LSP. So there, for each thread, you have to consider the call graph of procedure of each thread, and this LSP, it corresponds to the longest acyclic path in this graph. And I won't go into the details, but we have nailed down a procedure that has this complexity for the safety verification problem. And on a more practical note, we have implemented a prototype, an intern of mine. So Thomas Posch actually implemented the prototype, and we collected some experimental results. All right. So, and this is this work summarized in one slide. So basically, you have the whole universe here, and then you have this shape, which is the intersection of the language of the two threads, and you want to know if this shape is the empty set or not. So this problem is undecidable, but when you fix a window here, like the window given by this bounded expression, then within that window you can decide if you have the empty set or not. And from this picture, a natural question that you can now ask is, what is the general class of languages for which this problem is decidable? So can you go beyond intersection of context-free languages, for instance? So, and that's the question that we have studied, and the answer is yes. And I'm going to survey the results we have obtained. So basically, we identified a class of language for which the previous problem, so which is the emptiness with the intersection of a bounded expression, so for which it's decidable. And those are the language which are recognized by multi-head pushdown acceptors. So what are those multi-head pushdown acceptors? So just in a few pictures here. So it's an extension of the push-down automaton model. So you have a finite set of states. You have one stack. And then here what I have drawn is the input tape. And on this input tape, you have several reading heads now. And the way it's defined is that, so observe that the heads, they carry a color, like a yellow and green. And so does the state. And the way you should read it is that all the transition that goes out of the green state, they're only going to use the green reading head. And same for the, so if a state carry a color, all the transition that goes out of that state, they use the head of the same color. So for instance, one transition you may have is that when you are in Q1, which will use the green head, and that gamma is on the top of the stack, and that you have A4, that's the symbol to which the green head points to, like exactly in this case. So you have the green head points to A4. Then you can take this transition where you will read A4 and move to state Q2 and replace the top of the stack with W. So we have studied this extension, and what we have shown first is that, okay, this extension contains all context-free languages. That's rather easy to see because it's an extension with several heads. If you have one head only, you have the push-down automaton and all the context-free languages. So also it's easy to see that you can capture the finite intersection of those. And the idea is the following. If you want to capture the intersection of two context-free languages, let's say L1, L2 here, you use, so what you have one word on the input tape. So if you want to know if that word belongs to L1 and L2, so you first check that it belongs to L1 with, for instance, the yellow head. So you simulate the push-down automaton for L1 with the yellow head. And if the check succeeds, then you move on. You will again read the same word, but now you will simulate the automaton for L2 and check that it belongs to the language. So, and if you want to put more language in the intersection, you just have to add more heads to the automaton. So since we can capture finite intersection of context-free languages, we can also conclude that this model is good to capture the computation of multi-threaded programs. But they are not only good for this. So they are also good, for instance, to capture the execution of, now I will open a parenthesis, like sequential programs over integer variables. So and how it works, I give you some hint here to understand how you capture the computation. So think of the symbols on the input tape as actions of your program. So they do updates to the variable. So here you have two variables. So for instance, action A1, when you fire it, what it does, it's adding 1 to the variable 1, and it's adding 2 to the variable 2. Now if you have a sequence of those actions on the input tape, and you have to validate that it's an actual computation of some programs, what do you do? So first, you look at the sequence of action, and you ask yourself, can this sequence of action can be actually produced by the program? No matter if it's executable, just can it be produced by the program? Once you have done that, then you will do a second check. So you will check that this sequence of action is actually doable from the perspective of a single counter only. So for instance, using the yellow head, you will validate that the sequence of action of the tape is actually feasible. So and how you do this, so you read each action and you make sure that you can, you only look at one counter and you make sure that you can fire the actions. And then if you succeed, you go on and perform the check for the second counter. So and what I'm trying to convey here is that it gives you a really simple way to do the encoding because you really separate concerns. Like first, you just check that it's a computation that could be done by the program. Then you just check that it's actually a computation that is doable from the perspective of a single counter, and you completely ignore the rest. So, and then from the perspective of this one. So, and by the fact you have several heads, it makes the encoding simple.
Why do you have the fin here, the finite intersection? I didn't get that. What is that? What is the definition of that?
So it means that you cannot have infinite intersection of context-free languages. So because I only have finitely many heads in my model. So if I have k heads, I can encode. I know I can encode intersection of k context-free languages. So, and we could encode, it's a bit more complicated, but we could also encode systems where you have programs that communicate through FIFO queues, and they send each other messages through those FIFO queues. Okay, so what are the contribution of this work? So we have shown that not the emptiness problem of the language of such an automaton is decidable, because it's not, it's undecidable, but it's decidable when, again, you add one of those expression, those bounded expression here in the in your question. And in particular, we have shown that it's Cohen time complete. So rather surprisingly, the complexity collapsed to NP when you consider an expression like this, where each word consists of a single letter only. In that case, the complexity collapse. Okay, and how can you use those results? So first, as I've shown you before, so you can encode the computation of your system by using a multi-pushdown automaton. And then what you obtain from those these complexity results is a safety checker when restricted to sequences of action which are captured by such a bounded expression. So and you can enjoy many results, like it gives you, once you can do the encoding complexity upper bound for free, and also something that you have. I've shown you before in the slides that all the concerns are separate. So you look at one counter at a time and you validate that the sequence of action is fine for this counter. So you can actually mix different things in your model. So you can have counters and queues, and so as long as you can model it, you can really mix them together inside the model, and there is no problem. All right, so okay, so I told you that we did the encoding for FIFO communicating system. So that was actually the decidability of this problem for FIFO communicating system was proved before us, and that's the journal paper doing it. And so in our paper, which is way much shorter, so we do this and also many different models. So I'm just trying to argue that somehow things are much more simple when you use this this way to do things. Okay, now I will move to a more recent work on sequential programs. And here what I want to do is that I want to underapproximate procedural programs over the integers. And what I want to do in particular is to compute the summary of a function. Say here you have a function that takes in inputs ABC and returns two values x and y. What I want to do is to be able to characterize the relation between the input and the output. So in here I'm assuming that I have a program that manipulates only integer variables, and that I can, and for the logic I'm going to use to express the summaries, I'm going to focus on the Pressburger arithmetic. So computing summary, it's useful in various settings. So it's useful to do compositional verification. It's also useful to do equivalence checking, because if you wonder if F1 and F2 are equivalent, you can just compute their summary, and then you do a query in the Presburger arithmetic to know if they are equivalent or not. They can be used in termination proofs and also in refinement of abstraction. I will elaborate a bit more on that later. So my goal here is to compute summaries for procedural programs over the integers. And I want to do it precisely. So I remember, I give up on exhaustiveness, but I want to be precise. No, here I'm precise. So there is nothing over approximated. Okay, so you can check. There are some checks you can check that you are complete. So you can check that you are exhaustive. So if you can under-approximate the summary and check that you are exhaustive, so if you do that, then you know that you have an exact specification of the function and you could compare them. That's one possible use. So. Okay, computing those summaries, it's a difficult problem because you have many features that are in the way, like a recursive call, parameters, local variables, return values. So the methods that do over-approximation, they pretty much solve the problem. So for instance, I'm pointing here to the interproc analyzer that allows you to compute those procedure summaries. Okay.
Approximate anything by sigma star and there's nothing interesting to it. I mean, it has to be a little bit quantified, right? Okay, so it's always the same.
Okay.
So the way in which Interproc does is that they give names to the input variables and then it tries to keep runs an abstract interpretation numerical relational domain and tries to keep a relation between those names and the same values at the end, but that's please let's agree that it's not solved.
Okay.
It's a stronger.
That is a bold statement. So
What is not solved?
that over-approximation tool. So what I wanted to emphasize there is that if you give a program with recursive call, parameters, local variables, and all those features to an abstract interpretation-based engine, I'm not judging the quality of the output, but they will deal with all those things. They will deal with all those features. If you look at what is done for under-approximation or precise reasoning, they don't accept, they will simply reject the program and say, we cannot deal with that. So
for that specific tool, but you could just run testing techniques. I use it all the time and do that all the time. So, I mean, there has to be
yes.
here also.
Yes.
Under-approximation analysis in Microsoft.
It's called testing. That's what maybe I've been doing for like the last 40 years. And it's like we spend half of our R&D budget in this company, like in the rest of the software engineering community doing it, and that's called testing.
Okay, this tool doesn't deal with it. It rejects it. Okay. Okay, and I will explain what's our contribution here. And the way to explain it, I will use this, what I call the interpreter approach. So, and the idea is that instead of computing the summaries of directly of the program P, I will use an interpreter of the program P, and I will compute the summary of this interpreted program. And I won't explain that, but from the summaries of the interpreted programs, you can easily extract the summary of the program. And I will run FLATA on this interpreter. So as FLATA doesn't deal with recursion, I will have to provide FLATA a recursion-free program. So my interpreter has to be recursion-free. So Flata is a tool that's maintained at Verimax. So it's developed by Radu Josif, a colleague of mine. And it's following the line of works that he has done for several years. And before him, Jérôme Leroux, with the FAST tool, they have developed those techniques, which are they are called acceleration techniques. Okay, so I won't give you a definition of the interpreter. I will try to explain what's going on a simple example and how the interpreter works on this simple example. And I'll give it two shots. So on my first shot, I have interpreter A. That will be like what you expect from an interpreter. And the program it's going to interpret here, it's a recursive program. Here it's the function inc that takes in input parameter n and returns basically n plus 1. And the parameter must be greater or equal than 0. Okay, so interpreter A, when it interprets this program, what it's going to do is the following. So say I'm doing the interpretation for 3, which is the value of n. And I run the program. So I go around along the right branch, and then I reach the recursive call here. So what the interpreter does, so it will, I put this node in pink, it will remember the return address of the call, and then it will continue to interpret the code by diving into the call and interpreting the code inside the call. So, and here it continues like this until you reach the base case. And so which corresponds to the leftmost branch. And then you will return here from your call. So that's the interpretation that you would expect. So, and why I'm doing all this fancy development here, it's I want to give a notion here of budget of the interpreter. And the budget of the interpreter, I define it as the maximum number of pink nodes you have seen at any time plus 1. And it actually corresponds to the stack used by the procedure inc, because we have a 3 recursive call. All right. So remember that if I want to use Flata to compute the summaries here, I have to give an interpreter which is recursion-free. And the way I'm going to obtain a recursion-free interpreter, it's by bounding its budget. Okay, so for instance, if I give to the interpreter a budget of 4, so you can deduce that the execution that are going to be captured are execution that have at most 3 pink nodes. So basically, I won't visit anything that uses more than 3 stack frames. And Flata will return me this summary here. It will tell me that when n is given, it returns s plus 1, but only for, but you would have discovered that it holds only for value from 0 to 3. Okay, that's our first shot. Now we'll give you another interpreter that's gonna, with the same budget, it's gonna provide much more coverage than the one I have shown you. And the idea is the following. So it will again do like before. So we will go along the branch here, but at the point of a recursive call, we're gonna do things slightly differently here. So remember that before, what we were doing, we were diving into the call. So now, instead of remembering the return address, I will remember that I have to go into the call, and I will replace the call by an undeterministic choice. Here I'm very smart. I'm choosing the value 3, which is actually what I'm expected to have. And then I will just continue executing until the exit node of my procedure. Now, once I reach the exit node of my procedure, I have, what do I have to do? I have to validate that this guess I've just done is actually correct. So I will actually validate that the call to inc is correct. So I will validate that my guess was correct by continuing pursuing the execution. So, and I will do it the same way. All right. Now, if you think again about my definition of budget, is the maximum number of pink nodes you have seen on the screen plus 1. So here you can see that I'm using a budget of 2 only. My interpreter is using a budget of 2 only. And in this case, for inc, for the procedure inc, if I give to my interpreter B a budget of 2, which makes of the interpreter a recursion-free program, now Flata will return the entire summary of the procedure. Okay, so what we can observe when we compare the two interpreters is that with equal budgets, B is able to cover more behaviors than A. And also with the fixed budget, here the budget 2, for instance, B is able to cover runs of the original program that with unbounded stack usage. So clearly the interpreter B wins here. Okay, so now I will go over comparing A and B, but from a different perspective, which may make things more clear to you. So now I have this abstract program here, which has the same control flow graph as inc, but I've replaced all the statements just by labels. And to this program, I can associate now a context-free grammar. So and the way I do this is that each node in the control flow graph is associate a variable in the grammar. So just capitalize the label of the node. And for the transition, we have we apply the following rule. So for this edge from Q0 to Q2 with A on the label of the edge, I will have a production of this form. And the more interesting productions are those which are derived from recursive call. So in there, basically, so in call side Q2, you call F, and then you return to Q3. It's translated by a rule that says that you rewrite Q2 as Q0, which is the initial node of F, and then Q3. All right, so, and the language of this grammar here, it's A to the n, BC, which corresponds to the terminal case, D to the n. And if you think about a pushdown automaton that should recognize this language, so the pushdown automaton, it has to use unbounded stack space because when you read, because you have to remember that how many A's you read when you read the B's. Now let me again compare interpreter A and B. And what interpreter A does basically is to consider derivation of the grammar which are only leftmost. What it means that when I have several variables here in a derivation step, interpreter A will always rewrite the leftmost of those variables. And you can see here that, okay, that's the derivation of A2, BC, D2. And here the notion of budget I had before, so the notion of pink nodes there. So it corresponds to the maximum number of variable I see in a derivation step. So now if I consider interpreter B has more flexibility. So because when it reaches some step like this one, it doesn't have to rewrite the leftmost variable. It can choose any variable that he wants to rewrite. And for instance here, it can choose to rewrite variable Q3. And this is the derivation of the same word. And now if I look at the budget of this derivation, the budget of the derivation is 2, because I have at most 2 variables in the derivation step. And actually, if you choose the depth first derivation, with a budget of 2, you're able to recognize the whole language. But if you force yourself with leftmost derivation, there is no budget that will cover the entire language. So that's another perspective on the difference between those two interpreters. So as for the overview of the contribution, so what we have defined is a source-to-source transformation that takes in input possibly a recursive program over the integers, and it transforms it into a recursion-free program. I hope I convinced you that the transformation that we are doing is better than just simply bounding the stack usage in the original program. Because of what? Because we can capture executions with unbounded stack usage. So in our work, we have also shown some completeness results. So if the control flow path of your program, they can be shown to be contained in a bounded expression, and with some condition on the updates you do on the variables, Flattash will terminate and compute the summary, the precise and exhaustive summary for the program. And we have implemented the transformation and done some experimental results inside Flattash. Yes. So they have developed techniques already before to deal with loops. So when the loops of your program, they conform to a regular expression of this form, and that the updates on the variables are in satisfy some assumption, like Radu and also Jérôme Leroux before, they already took care of computing the effect of those loops. You can have tests in them, and when you have nested loops, you have no guarantee anymore. So, okay, I see what you mean by disjunction. Yes, there, when you start to have on one location 2 self loops. Yes, yes. So either like the program that's given to you already satisfies this assumption, or you just force the assumption on the program. So you pick up an expression like this, and you do the intersection, and then you try to compute for this. It's an under-approximation. So since you give up on exhaustiveness, it's okay. Okay, so what to bring home today? So I told you about under-approximation technique, which is about more precise reasoning. And I've presented you two family of under-approximation techniques. So there is this budget idea on the derivations, and there is this idea about those expressions, those bounded expressions. So for this work about the budget constraints, it's rather easy to come up with an under-approximation, because you just need a number, right? You just need a budget, you say 5, and then you can start to run your analysis. So now here for bounded expression, so you need somehow I'm assuming that the user is giving this expression to you. And so my first paper about those bounded expressions was in 2010, and now I can tell you by experience that it's not easy at all to come up with those expressions. So, and there, okay, I will suggest the following. So I don't think that the user will ever be able to come up with those expressions. But they can come up from somewhere else. And I think they can come up in the context of abstraction refinement. So just very quickly, abstraction refinement. So what you do, so you start with a coarse model of your system. you find a counterexample that, if it's a real one, you're done. If it's a spurious one, then you will basically, what you want to do is to eliminate this imprecise behavior from your system. And the way you do it is by recovering precision in the model. So, and what the Seaguard technique does, it's to recovering precision one counterexample at a time. It works well in many cases, but in some cases you may diverge. And in particular, you may have something like this. So the first counterexample doesn't go through the loop. It's just going from the left part to the right part. Then you do refinement. Then you have that the second counterexample goes once through the loop. You refine. Then you have another counterexample that goes twice through the loop, etc. So there, I'm confident that this technique about that use the bounded expression here could be of some help. And the idea is to use precise reasoning. That's what is provided by the reasoning about those bounded expression, to eliminate not one counterexample, but many of those at once. And the idea here will be simply, it's just to give you the intuition, so to associate a word to each path here, and then you can see that if I can do precise reasoning along such a bounded expression, then I will have eliminated all the counterexample that just go more and more often through the loop body. So that's just the intuition. It's something I have to explore. All right, so that's basically the big picture of my research. So I have told you about those two lines of works, about multi-threaded programs and also the programs over the integers. So I also have done some contribution on event-based asynchronous programs, and more recently on parameterized systems. All those work, they have used some under-approximation. And so we have used those bounded expression here for multi-threaded programs. But in all the others, we have used this idea of bounding the budget of the interpreter, or bounding the budgets of the derivations that we look at. And this under-approximation by using budget, it's actually, in many cases, not an under-approximation. So for event-based programs, or in the case of parameterized systems, we're able to show that if you take a budget which is high enough, you will actually be complete for the question that you are investigating. In the case of programs over the integer, so in general it's not complete, but as I told you, we have a completeness result when the control flow is captured by a bounded expression. And we also have done some preliminary implementation work for those, except for the parameterized system case. Thank you.